Hello and welcome back. In the last video we took to r/electronics and found this post where we helped a user by exploring some theory behind the operation of 7-segment displays. We made a series of simplified logical expressions which would provide us the framework to display the digits 0 to 4 using just 3 inputs. But how can we implement this in real life? In this video we'll see if we can arrange a circuit to accomplish this on a breadboard using real components. But before we do so, why don't you smash like and subscribe? So before we get started, we have to do a quick review on breadboards and how they work. Breadboards are a popular tool used to test and prototype electrical circuits. We can see that a breadboard is made up of many holes, and we can actually use these holes to insert and connect various electrical components. On the top and on the bottom, we have our power supply rails, and in the middle we have our vertical nodes. This is to say that each of these lines, as illustrated, represents its own common point. So if we connect a component to a hole, it will be directly connected to all of the holes sharing the same line. And a common practice is to connect the upper and lower power rails as illustrated, so that you can power your components in a more convenient fashion. And so now that we have a basic understanding of what the breadboard is, we can move on to start adding some real components. And the components we'll be adding will include a 7-segment display, and all of the actual logical components according to the logical expressions we created in part 1 of this video. So the first thing we need to do is to add a DC power supply to run the circuit. We'll be using this variable power supply on the upper left and setting it to 5 volts as per the project requirements. We'll connect the positive and negative leads to our upper power rails as shown, and we'll add some jumpers to supply 5 volts to the lower rails as well. And so now that our power rails are live, we can actually start building the rest of this circuit. And we're going to start with the 7-segment display. And first, we're going to see if we can turn on some segments before we add the logic circuit. This is a common cathode display, which means that all of the negative terminals on the internal LEDs are connected together. So that means if we connect one of the common pins to our negative power rail as shown, all of the segments will have a good ground connection. But this doesn't mean that we're ready to turn on a segment. If we connect 5 volts directly to one of the segment pins, the LED will actually explode because the current will be too high. And this is why we need to use current limiting resistors. I've picked a value of 200 ohms because at 5 volts this makes a current of 16 milliamps through the LED as indicated by the power supply. And this is a good value because it's less than the 20 milliamp maximum but provides enough current for a good brightness. So we'll add a resistor to protect each of our segments as shown, and we can see that they all light up without exploding when we provide a high signal. But we still need a way for the segments to light up automatically. So now we're ready to start by hooking up our digital inputs to drive our logic circuit. And to do this, we'll be using this multi-switch on the left for our inputs. And although it's made up of 4 individual switches, we'll only be using 3 of them, because as we covered in part 1 of this video, we only need 3 bits of data to count to 4 in binary. So we'll connect each of our digital inputs to 5 volts as shown. And this way, if we close one of the switches, the high signal will appear on the other side as well. So this works fine if we just want to switch a load on and off, as you can see. But because we're going to be using these signals to feed a logic circuit, we're going to need to add some pull-down resistors. And to do this, we simply just connect the resistor between the other side of each switch and ground. This way, when the switch is open, the downstream side will be connected to ground and settle at 0 volts. And that will be a nice clean binary signal feeding our logic circuit. And for our pull-down resistors, we can use a high value of resistance because we don't need them to conduct any meaningful amount of current. So I'm just going to pick a value of 1 million ohms, or 1 mega ohms, to keep the power consumption low. And so now we have these 3 input points as illustrated in green that will change between 0 volts and 5 volts depending on the state of each of our switches. The one on the top represents our most significant bit with a weight of 4, so we'll call it input A. The next one down is input B with a weight of 2, and the one at the bottom is input C with a weight of 1. So now we're ready to install the logic circuit, which will be able to decode this 3-bit input and drive each of the 7 segments. So here's the actual logic that we're going to try to build. If you want to know where these expressions came from, I recommend watching part 1 of this video, which covered the entire theoretical side of this project in detail. And if you did watch part 1, you might notice that the list looks a bit different than it did before. And that's because I've relabeled the segments according to the more standard arrangement. The logic hasn't actually changed. So I thank you for the feedback, pointing out the error I made in the last video. And now, keeping this logic in mind, we can move on to the fun part and actually connect the actual logic gates to the circuit. The first thing we're going to do is set up our NOT gates, also known as inverters. Because as indicated by these overbars, each of our 3 inputs will need to be inverted. The inverter we will be using is the 74HC04, so we need to look at the datasheet to figure out the connections. We can see that the supply voltage needs to be between 2 and 6 volts, so our power supply of 5 volts should be perfect. We can also use the datasheet to find our pinout. Here we can see the power supply connections. VCC will connect to 5 volts, and ground will connect to 0 volts. We can also see the locations of our inputs marked with A's, and the outputs marked with Y's. We can also see that the maximum input current is 20 milliamps per pin. Now we could use a current limiting resistor if we wanted to at each of the input pins to reduce the risk of damage, but we shouldn't have to do this because we're going to be operating within the recommended voltage range. And because these ICs have a very high input impedance, the input current will be kept very small as long as we operate within the recommended range. And the last thing we need to note from the datasheet is the maximum output current of 25 milliamps per pin. This won't be a problem for us either, as we'll be feeding these inverters directly into other logic gates, which also have high input impedance. So the output current will be kept to a small level. And now that we understand this IC a little bit more, we can actually hook it up to the breadboard. First of all, we can see the power and ground connections at the top left and bottom right corners respectively. And this is based on the diagram we saw in the datasheet. And we can also see, if we look at our power supply, that this chip is drawing 17 microamps just in standby mode, which is actually a very tiny current flow. And as we said before, we'll connect our inputs directly to each of our 3 input pins on the IC as shown. We can see that even with all 3 of our input switches closed, the total current is still only 35 microamps. This is again because of the chip's high input impedance, which keeps the current at a safe level as long as our supply voltage is not too high. So now all we need to do is to connect our outputs as shown. Each of the blue leads represents the opposite of the respective green input. Therefore, the one on the top is not A, the next one down is not B, and the one at the bottom is not C. And that's really all we have to do to set up our inverter. So now we'll get to placing the AND and OR ICs onto the board, and we'll create logic circuits for each segment one at a time. On the left, we have the 74HC08, which contains the AND gates, and on the right, we have the 74HC32, which contains the OR gates. You can see that the power and ground connections are the same as we had for the inverter IC, and if you check the datasheets, you'll find that the diagrams are the same as well. They also have the same supply voltage range of 2 to 6 volts, which makes it very easy for us to hook these things up to the same board. And with all these components hooked up, if you look at the power supply, you can see the current draw is still very small. So now that we have all the ICs we need on the board, we'll get started with connecting them together. And we're going to start with segments A and D. This is because we found in the previous video that since we're only counting to 4, segments A and D will always be on at the same time. So we can connect these pins together using this orange jumper, as they'll only require one logic circuit. And this is the logical expression we came up with in the first video to drive these segments. It says that these segments will be on when input B is on, or when both inputs A and C are off. The positive sign represents the OR function, and the multiplication represents the AND function. So we'll need one OR gate and one AND gate. And we can see how to connect these ICs by the pinouts in the data sheets. Both the OR and the AND chips have the same arrangement, where the individual logic gates are made of sets of 3 pins, 2 inputs followed by an output. So to create our AND function with not A and not C, we simply connect the inverted A and C inputs to our AND gate as shown in orange. Now all we have to do to finish the expression is to connect this AND output with our B input. And we'll connect these together through an OR gate, again shown in orange. And we can connect the output of this OR gate directly to our 2 segments with one final jumper. And we can see that the segments are on. And this is what we expect because all of our inputs are off, so we want to display a 0. If we turn on our least significant bit by closing switch C, that means we want to display a 1. And our output will be off according to our logic. So far everything is working. But we'll go through the entire sequence at the end once we have all of our segments connected. For now, we'll move on to segment B. And as we can see, we came to the conclusion in the last video that segment B is equal to 1. In other words, segment B should always be on. And this is because we're only counting to 4 in this project. So all the digits 0 to 4 share this segment in common. So we'll simply connect the high signal to our B segment resistor, and we'll see that it turns on just as we expect. And this segment will stay on regardless of our inputs. And this wouldn't be the case if we wanted to count all the way to 9, but that's a topic for another video. And so here we can see the logic we created for when to turn on segment C. And we want segment C to turn on if input C is on or if input B is off. So segment C is equal to input C or not input B. So all we have to do is to connect our C input and our inverted B input directly to the second OR gate as shown in pink. The output on the right can then feed our segment resistor directly. And we can see that because all of our switches are off, we should be seeing a 0 display, and now we have that one extra segment as part of our 0. If we wanted to display a 2, for example, we would turn on only our B input, which has a weight of 2, and we can see that the C segment turns off, just as we would expect. And again, we're going to cycle through the whole combination of numbers later, but for now, we'll move on to segment E, as we've already connected segment D because it shares the same logic as segment A. So the logic we created for segment E states that E is equal to A bar and C bar. So we just need to drive this segment from the output of an AND gate fed by our inverted A and C inputs. However, as we can see, we've already created this particular AND function in the logic for segments A and D. So we can simply piggyback off the output of this AND function that we already created and connect it directly to our E segment as shown in green. And we can see that we're now one segment closer to displaying the digit 0. And we're also now only one segment away from being able to display a 2 when we turn our B input on. And this leaves us with only 2 segments to go before we can display all of our numbers. So moving on to segment F, here is the logic we created in our last video. And we can see that we need to make another AND gate, but this time with the inverted B input and the inverted C input. And this way, the segment will only turn on when each of these inputs are off. So we'll take these yellow jumpers from our inverted B and C inputs and connect them to a third AND gate as shown. And we can connect the output directly to our F segment resistor, and we can see that now we're displaying the entire digit 0. And if we want to turn on our least significant bit, we can now see a 1. But we can see that we still have to create the logic for the middle segment because we can't yet display an entire 2 when we provide the corresponding binary input. So we'll now move on to our final logic for segment G, which states that segment G is equal to input A or input B. So all we need to do is to create one more OR gate with A and B as the inputs, and we should be good to go. So all we have to do is to connect the non-inverted A and B inputs to a third OR gate as shown in purple. We've also connected the output of the OR gate to our final segment. And so this is what our completed circuit looks like. So now let's watch the display as we input 0 to 4 in binary. We can see we get the 0 when all of our inputs are off, but if we activate our least significant bit, we can see that a 1 is displayed. And we see a 2 when we input a binary 2, a 3 for a 3, and a 4 for an input of 4. Now this is really cool, and we've accomplished our goal, but this is as far as the circuit can take us. You can see if we input a 5, then all the logic goes out the window. The same will be true for the digits 6 to 9. And this is because the request for this project was to count to 4 specifically, and so we based all of our logic around that. So if you want to see an improved counter that can count all the way to 9, please like the video and subscribe to the channel, because these videos do take a while to make and I do need your support. And please leave a comment if you have any questions or any other topics you would like me to cover. And thank you for watching.